Okay? So you'll be expected to be able to draw this yourself. All right. So here are our rules. And I'm going to kind of sort of translate so we can get through quicker without just having to read. Basically, what this says is we go from highest to lowest within each energy level. So in 2P, which we already know that, and we showed you the exception and we showed you how to get to that. But the reason that this is here is because we know exactly what principle this is. So going from lowest to highest energy level is called the filling up principle or the off ball principle. Okay. So basically, going from lowest to highest means going from this way to that way. Off ball principle tells us we're going to fill one electron at a time in each orbital until we finish filling, until we get to the desired number of electrons in the orbitals. So that is known as the off ball principle. It's also sometimes called the filling up principle. We already told you that orbitals of the same sublevel have the same energy. So rule number 1, we go from lowest to highest. Rule number 2 is we cannot have more than 2 electrons in an orbital. We saw that the other day. And this is called the Pauli exclusion principle. Lowest to highest off ball, no more than 2 electrons in the orbital, Pauli exclusion. And then finally, the last thing we have to remember when filling our electrons is Hund's rule. Which basically tells us that when we're filling electrons in the same energy orbitals, such as in the 2p orbital, we can't just come in and start putting electrons 2 at a time. Can't do that. We have to fill 1 electron at a time in each one of these degenerate orbitals before we can come back and start pairing them up. And when we do pair them up, remember, because of the m sub s quantum number, we have to pair them in opposite spins. Okay? All right. So those are our rules. Lowest to highest energy, only 2 electrons at a time, singly before we pair. And that's all we need to know to be able to write electron configuration and draw orbital diagrams. Okay? So let's get to it. Let's see what's on the next page before I start. All right, so let's look at an example. Aluminum. Let's take aluminum for an example. The first thing we do is we look on the periodic table and we look at the atomic number, which tells us the number of electrons, right? So how many electrons do we have in aluminum? Okay. Is that the atomic number of aluminum? Okay. So we're not looking at the number of valence electrons. We're looking at the actual number of electrons. That is the atomic number, which is 13, right? So that has 13 electrons. So now we have to fill 13 electrons and do our electron configuration and our orbital diagram. Which one do you want to do first? The orbital diagram and electron configuration? Okay, let's do electron configuration first. We know our order. So 1s, we can go ahead and put 2. All right. The next one is 2s. We can go ahead and put 2 electrons there as well. The next one is 2p. We can put our full 6 there. That is 6, 8, 10 electrons. Now we have to put 3 more. What's the next energy level? Okay, and we're going to put 2 there. And then what? 3p1. Okay, so that's our electron configuration. Now let's draw our orbital diagram for that one. So Some people draw boxes. I kind of like to draw blanks because it takes less time. But so we know what energy levels that they're going to occupy: 1s, 2s, 2p, 3s, and 3p. Remember, S has 1 orbital, P has 3, D has 5, F has 7. So we're going to go ahead and put our 2 here, put our 2 here, in opposite spins. We can't just go ahead. We wouldn't, if we didn't already have the electron configuration, be able to go ahead and fill these. We have to fill them parallel first. 1, 2, 3. And then we come back and fill them, pair them up with opposite spins. So that's our 10 electrons. This is our 12. And now this is our 13th. Okay. Let's do one for, let me look at the periodic table. Let's do one for phosphorus. Mm-hmm. This is the orbital diagram. So as you can see, you can look at any of the orbitals and see where the electrons are in both of these. Uh-huh. You can do either both, one or the other. And I'm going to give you some, we're going to do some like problems together to kind of give you an idea of what you'll be expected to know how to do. Let's see. Phosphorus. How many electrons does phosphorus have? So why don't you do that one? Try to do that one without looking. If you're absolutely lost, you can go ahead and look. Is that right? Two, four, two. Not too sure, to be honest with you. Somebody said 35. The more practice you do, the better outcome you have. 10 max. 5 orbitals with 2 electrons in each, so you can have a maximum of 10 electrons in the d orbital. It's probably going to be due Wednesday the 10th. Okay, so any questions about this one? Did everybody get that? Okay, so should we go back through it together then? Let's do that. All right. So we're going to write in order. 1s can have 2. That's 2 electrons total. 2s can have 2. That's 4. We continue filling in order. 2p can have 6. So that's 12. And 3s can have 2. That's not what I had. Ah, so you did have it right. What did I have? I was testing you. No, actually, I don't. My mind was somewhere. I was wrong. This is the correct way. 1s2, 2s2, 2p6. So trust when you know what you're doing. Trust your knowledge. 1s2, 2s2, 2p6, 3s2, and 3p what? Okay. All right. So that's 2, 4, 10. Oh no. 12, 13, 15. All right. So 1s in the orbital diagram is going to have 2 electrons. 2s is going to have 2. 2p is going to have paired singly, and we have enough to go back and double them up. 6. 3s is going to have 2. And 3p is going to have 3. And we didn't notice we did not put them like this. That would be wrong because we have to put them in single before we go back and double them up. We also didn't put them in like that because the spins have to be opposite. You stretching? Okay. All right. So that's the basics on using the rules to do an electron configuration and draw orbital diagrams. Are in F, Florian? Oh, 14, sorry. The F orbital has 7 suborbitals, and each one can be occupied by 2 electrons, so it can fill up to 14. The F orbital. D is 10, F is 14. Mm-hmm. Mm-hmm. Yeah, that's the order that they go with. It's supposed to, it correlates, you see, it's kind of hard to see the order there, but I can hear the right. It correlates with the one that we showed you on the next slide that we wrote out ourselves. So, but that's how it looks if you write it out in terms of an energy diagram as it goes up in energy. Okay. All right. So now let's talk about valence electrons. The next slide that we have here, just kind of sort of, this is the next slide is blank, but the next slide up just shows us some examples of electron configurations and orbital diagrams for some selected atoms, selected elements. So we have one for lithium there, we got one for beryllium, we have one for boron, we have one for carbon, and it just shows already some electron configurations and orbital diagram notations that have already been done that you can just go back and refer to. And these are also several of them in your book. If you get confused, you can always go back and refer to, I forgot, I wrote a page down for you last night, but I didn't bring it with me. You can always go back and refer. Now let's talk about valence electrons. Okay, now how do I want to approach this? Let me show you the valence electron situation on an electron configuration. So this is a generic electron configuration. What element is this the electron configuration for? It's got 16, so it's the electron configuration for sulfur. All right, so if we were to draw out the orbital diagram, I'm just going to draw blanks, okay? So you know that these are supposed to be boxes. I'm just trying to go a little bit faster here. They don't have to be boxes. You can, as long as you're denoting an orbital. Okay, so this is the electron configuration for sulfur at the top, the orbital diagram notation for sulfur at the bottom. If we look at the energy shells that are completely filled to their maximum capacity, what energy shell do we have there that's filled to maximum capacity? Mm-hmm. So let's look at the whole energy level. So look at energy level 1, energy level 2, energy level 3. So energy level 1 is filled to its maximum capacity. Energy level 2, is filled to its maximum capacity, but energy level 3 is not, right? Because we can still have 3D electrons that have not been filled yet. So these electrons that have been filled to their maximum capacity are what we call core electrons. And we don't really draw energy diagram orbitals like this anymore. But if you could imagine that each one of these little rings represents an energy level. Closest to the nucleus, core electrons. So these are filled all the way up to maximum capacity. The ones at the highest energy level that are not all the way filled are called valence electrons. And down here you have writing that summarizes that. It says the electrons in all the sublevels with the highest value energy shell are called the valence electrons. Energies in the lower energy shells are called the core electrons. But basically, you look for the one that's at maximum capacity. And I'm going to show you how you can find it on the periodic table as well. But this is the basic definition. The electrons, the energy levels that are filled to max capacity are the core, and the ones that are not on the outer shell, the higher energy levels that are not yet completely filled, are called the valence electrons. Understanding the behavior of valence electrons is critically important to everything that chemists do, because it is these valence electrons, these electrons that are on the outer perimeter of the atom, that determine everything that the atom is able to do, what type of reactions it can participate in. All of its physical and chemical properties are pretty much determined by the valence electron. So this is why we go to such a length in defining them. Okay, so everybody got the basic definition of a valence electron? Now I'm going to show you a different way to do electron configuration based on the definition of valence electrons. Okay, so let's look at neon. Neon has 10 electrons. Excuse me. Thank you. Okay, this is how we write the electron configuration for neon. Okay, so if you think about that, that is a completely filled shell, right? That's 10 electrons, a completely filled shell, and all of those are pretty much, well, it's a completely filled shell. So what we can do is, if we don't want to have to write out all of the 1s, 2s, 2p, 3d, whatever, blah, 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 we can then take whatever noble gas. See, this completely filled shell is a characteristic of the noble gases, remember? They all have a completely filled outer shell. And so basically, they don't like to participate in a lot of reactions because they don't have any really free electrons floating around, right? So basically, we can now take neon and use it when we get ready to define the electron configuration for any element higher than neon. Yes, yes. So any noble gas that precedes the element that you're trying to write the electron configuration for can be used as its shortcut, and then you can go and fill in the remaining valence electrons. So let's look at sodium, right? Sodium has 11 electrons. Mm-hmm. So generally what we would do is what he just said. We write the 1s2, 2s2, 2p6, 3s1. But now that we know that, hey, we got a shortcut, this is equal to neon, now we can come in and we can substitute this right here and just say, okay, we're going to say, okay, this has all the electrons that neon has in it, in its core, plus 3s1. Just the last row, just the ones in row 8 that you can use. Mm-hmm. Well, unless they ask you to specifically, I need to look at the way that the problems are worded on the homework, but if they ask you for electron configuration anytime, you should be able to specify the core noble gas configuration plus the valence electrons and just write it out like that. Everybody cool with that? All right, so let's look at another example on the next slide of that. Okay, everybody's not quite done writing yet? Mm-hmm. Let's see, what is magnesium? Absolutely. For magnesium, it would be what? Say it. Neon in brackets? Absolutely. And you can do that all the way up till you get to chlorine and just add an electron each time. Then when you get to chlorine, your next noble gas is going to be argon. So then you can start doing that same thing using argon as the inner core for your things in the next row, which are potassium, calcium, scantium, titanium, vanadium, etc. Okay, so let's look at a couple more that do that. This is one is already written out for us. So basically, this one is using krypton, which is a noble gas in the 4th row, and it has 36 electrons, 28 core and 8 valence, and its electron configuration is listed here. So we were to actually want to write the electron configuration for the next atom up, the next element up, which would be rubidium. And we could just take that krypton core, which is right here, and then add the 5s. So what I want you to do, let's just go back and do the ones that we just did a few minutes ago. So I'm going to go back up. Is everybody done writing on this slide? I'm going to go back up a little bit into these. And let's see what we would do using the core configuration notation for these, for aluminum. It would be neon, right? And so would phosphorus. It would also have neon. Uh-oh. Okay. Let's see. Did we do anything else? How about sulfur? Sulfur would probably also be a neon. So, same deal. Alrighty? So that's how you use the core electrons in the noble gas configuration to be able to um, write your shorthand notation. Now, when you do shorthand notation, notice that if you're asked to identify what are the core electrons and what are the valence electrons, it's very, very easy because all you have to do is look at whatever's outside of that. Outside is valence. Right. Outside is valence, inside is core. All right. Questions? We good? Right here? Okay. The valence electrons are everything in the highest energy shell that's not core. So the valence electrons would be the 3s and the 3p. So you would have a total of 3 valence electrons right here. 3 valence and 10 core. And you could be asked how many valence electrons you have or how many core electrons you have. Down here, you have 10 core again. I'm messing this slide completely up. And you have 5 valence. And I really want to get to where we can do some examples from from the back of the book. All right, we're gonna get there. What time do you have here? Okay, we're gonna get there. The lesson, now we know the rules. We know how the orbitals electrons fill up the orbitals. We know how to write electron configuration, orbital diagrams. We know how to write the shorthand notation. We know how to identify core electrons. We know how to identify valence electrons. Now, and that is basically taking us to the next step. We know that we said when they put this periodic table together, that it's a pretty amazing feat here, that everything has a pattern. We said that it tells us, it's so predictive. It tells us so many things that we just couldn't imagine. And so we can actually use the position that the element is in on the periodic table to identify valence electrons, to identify what we expect the electron configuration to be, orbital diagram notation, etc. So you don't necessarily have to do all the counting. If you can just look at, based on where it's located on the periodic table, you can be able to predict a lot of these things. So this is what I'm going to tell you, that the group number corresponds to the number of valence electrons. I'm going to show you in a minute on the periodic table. The length of each block that I'm going to show you tells you what the max number of electrons is that it can hold. And the period number corresponds to the principal energy level of the valence electrons. Let us look at what I'm talking about. First, I'm going to show you what I'm about to point to this block right here, and I'm going to show you what they look like side by side on the next slide. This is this is on page 7 that I'm drawing on right now, but where I'm getting ready to point to is going to be on page 8. Okay, so this is what I'm going to show you on page 8. So if you take these and you sit them side by side, you see they're spread out over here, and you see that we've got 1, 2, 3, 4. If you look at these numbers here, 5, 6, 7, etc. If you put these side by side, then you see something. You see that the order that the 1 and 2 energy levels fill. And you also see the order at which the S block and the P block fills. So looking here, this is our S block. Everything that's over here corresponds to what we call our S block on this side of the periodic table. And I'm gonna clarify in just a second. Just bear with me. Everything on this side right here is called our P block. And that corresponds to these right here. So basically, hydrogen, everything except hydrogen and helium are pretty much always going to be the exceptions because they have so few electrons. It's only going to occupy the s orbital. But everything over here is our s block. Everything over here is our p block. And if you look at this slide, you can see why. The highest number of electrons filled here is 2s. The highest number of electrons filled in everything over here is 2p. Now let me go back to that one that I was just playing with. So if you can look at, it would be nice if we had this slide in color, but these are the designations, these are the zones on the periodic table that tell you these things. So over here, as you can see, set the s orbital is the highest orbital field. It doesn't matter what row you go to, the s orbital is the highest orbital field. Over here, in the pink, the p orbital is the highest orbital field. Doesn't matter where you go, down or up in a family or group, the p orbital is the highest field. Of course, we're going to use helium as the exception. You with me? Down here is what we call our transition elements. We also call these d block elements sometimes because it's the d orbitals that are the highest field. So that's the first thing. Right. It's always going to be in the S because it only has 2 electrons. Helium is supposed to actually come over here with sit next to hydrogen, basically. But it actually acts as a noble gas because it is completely filled on the outer shell. So it goes over here and sits on the periodic table with the noble gas family. So what else can the periodic table tell us? It also tells us the number of valence electrons that is in this block. So if we happen to fall on beryllium here, we know that the highest energy subshell is the S. And if we happen to fall on, we know we're in the S block, so the electron that is in the S, we can identify by the group number, which is 2. And the energy level, we can identify by the row value, which is 2. So if I tell you, look at periodic table and tell me what are the valence electrons in the beryllium atom, you'll be able to look at and say, okay, this is in row 2. So it's going to be 2. It's over here in my S block, right? So it's going to be S, and it's in family number 2. So I know it's going to be 2s2. If I ask you to do it for, let's go over here and play with one of these pink ones. Let's do it with oxygen. If I ask you to do it with oxygen, you know, okay, oxygen is on row 2. So it's going to be energy level 2. It's over here in the P block. So we already know it's got the 2 S's completely filled already. So we know that the rest of them have to be over here in the P block. And we know that it is in group 6. So we know total valence is 6. So now The rest of them have to be 4 in the is 4 in the p orbitals. So the total valence electrons is 6. The highest shell occupied is p, and we can tell that by this number right here. What about calcium now? Let's go back. Let's play with a couple of these. Here's one that it gave you as an example. Let's look at chlorine first. Okay. We can do several things with chlorine. All right. We can use the periodic table to find its valence electrons. We can find its electron configuration. First, let's find its valence electrons. How many valence electrons do we have? And those are in energy level what? 3. So there's 7 valence electrons in energy level 3. How will we go about writing the electron configuration for that? There you go. And then 3s2. And the rest of them are in the p block. When we how do I put this? When we start fooling around down here in the transition metals, we are let's pick one. Well, I'm gonna let you go ahead and write that, and then I'm gonna tell you something else here. When we're talking about valence electrons, we're not talking about the order that they fill. So even if we have, let's say vanadium, which is located right here. Even if we have vanadium, which would have the inner core, right? And then it would have the 4s2, and then the 3d3, right? Because for the ones in the transition series, we don't have numbers above them, so we're going to count ourselves. And you see it's 10, so it's 10 total electrons that it occupies in the D block. Perfectly. It's 6 over here. 1, 2, 3, 4, 5, 6. And it's 2 right here. Corresponds exactly to our orbitals. But what I'm trying to get to tell you is that if I gave you this and said, hey, identify the valence electrons, we're not talking about order of filling. We're talking about the electrons that are actually in the outer shell. So although the order of filling was 4s filled before the 3d, the actual valence electrons are the 4s because they're in the highest value energy shell. The highest N value, okay? The order of filling does not affect which electrons, where the orbitals are located. Okay. So if we got 2 electrons in that 4 value energy shell, that was a lot of words thrown together. But if we got a 4s there, that's where your valence electrons are located. And if I had to go over here, and if I got 4s2, 3d, let's see, 10, and 3p2, it's still 4s. It's my highest. Okay, so that's what we mean by S block elements, P block elements, D block elements. And down here you got your F block. They have 14, but we're not going to really mess with those too much. In this one right here. Oh, yes, in the one that I just identified, yes, it only has 2 valence electrons, yes. I was just playing around and giving you an example of one right here. If we were writing the electron configuration for this element right here, which if we look on the periodic table, it is germanium. If we were writing an electron configuration for germanium, that's where it would fall. Okay, so I want to give us a lot of practice on this. Was anybody able to pull up the video with the sample problems that I put up? Okay, so I'm gonna try to, if we run out of time here, I'm gonna try to do that again so you can have an opportunity to see a lot of this in practice. I'm gonna put some of the problems on the back of the book. I'm gonna ask you to try them first to practice, and then I'll do the solution to them for you so you can get an idea. But for right now, what time do we have? I think we still got a little time to play. Ooh, okay, still have 10 minutes. One more thing I want to tell you. There's always exceptions to everything in chemistry. So those are the general rules that I gave you on the order of electron filling. But down here in this D block, where the transition metals are, there's sometimes some irregularities. We expect the electrons to feel a certain way, but experimentally, when we go in the lab and we do an experiment to see if it syncs up with what we expect, it doesn't necessarily do that. And so there are some exceptions to that filling order, and this is them. Okay, so you need to memorize these. You need to know that these are the elements that in nature don't fill the orbitals in the order that we expect them to based on our prediction. And this is what they actually do. Okay, so let's look at a couple of problems right quick just so we'll see what it is we'll be expected to. I'm going to read them to you for the ones that I know we know how to do already and we're not going to do them, but I'm going to give you the number of them. These are the only ones. This right here. So basically, we expect, if we were to write the electron configuration, let's look at the periodic table. Let's say for chromium. Let me look at my periodic table here. What is the atomic number for chromium? We would expect to go in and write, and argon is the noble gas that precedes it, right? We would expect to go in and write argon and then go to the next level and then start talking about, okay, 4s2, and then go ahead and fill the remainder up with 3d4. But it doesn't happen like that in nature. And so the only thing we can do is memorize that this is an exception. Right. So instead of doing this, chromium feels like this. Right. Exactly. We'll see. It's probably you're gonna put D4D. Because this is expected. This isn't what actually happens. Now, what was your question again? Mm-hmm. Well, basically, you can just say that these don't completely fill the 4S. They fill only one of the 4S, and you can add for these. Yeah. Not really sure. It has something to do with the shielding and penetration. Some type of the interactions that the electron experiences. There are some some more detailed explanations for it, but I honestly have forgotten them from graduate school. They are, but they do go back to your shielding and penetration of your electrons as they try to um, come to the nucleus. Okay, so let's look at a problem right quick. Reinforcement for this, you can look in your book on page 344, and it has some more examples of solved electron configuration and orbital diagram problems. Page 344. All right, so if we look at the back of our book, we can see that these are the type of things that we might be expected to do. I'm going to just go ahead and tell you these types of things, and I'm going to give you the numbers and let you go and try them, and then I'm going to try to put the solutions up tomorrow. Okay, so the type of things that you'll be expected to do are problems 41 through 46 basically are pretty much the same thing, 41 through 45. So look at 44 and 45 at the back of your chapter on page 375. Yes, it's the same. Actually, I got mine off the electronic. 375. And you should be able to do 45, which asks you to write the electron configuration, represent the core electrons with the symbol of the previous one. Um, of course. I won't be in my office hour today. My office hours tomorrow are 9 to 11:30, and then it resumes on Thursday 11. Yeah, after 11 to 12. 46, you should be able to do. You should be able to tell what element goes with the particular electron configuration. 47. Those are things that, those are just basically writing electron configuration. If you don't know how to write electron configuration, you should practice with those. And I also have problems already up on Blackboard that kind of show you the solutions to a couple of these. Um, 49 you should be able to do. And 51. So on page 375, if you want to practice and make sure you can reinforce what we learned in class today, this is not due or anything. This is for your benefit. For page 375, problems 45, 46, 47, 49, and 51. Those are good practice problems for you to reinforce what we learned. And I will try to put the solutions up to these tomorrow, probably around noon. Okay? And so I will see you in